next talk, which will be by Christina Eilers on the formation and growth of supermassive black holes. Christina, go ahead, and I'll give you a 2-minute warning.
Okay, thanks, Larry. Yeah, thank you, first of all, to the organizers for giving me the opportunity to present my research here. My name is Christina Eilers, and I'm currently a postdoc at MIT, and I'd like to show you some of my work on the formation and growth of supermassive black holes in the very early universe. In the last few days, we've seen a lot of very interesting talks about studies that use high-redshift quasar or galaxy spectra to set constraints on the intergalactic medium, on its neutral fraction, its evolution during the epoch of ionization, and so on. And I'd like to turn this question around and say, what can we actually learn about the quasars? But in order to do this, we look at how the IgM in the vicinity of a quasar responds to the ionizing radiation that the quasar emits. And so this is a radiative transfer simulation post-processed on a cosmological simulation. In the top panel, neutral gas fraction of the IgM as a function of distance from the quasar. And in the bottom panel, it shows the spectrum of the quasar as we would observe it. So the gray dashed line is the continuum emission from the quasar, but this is at redshift 6. What we actually observe is this black line. And if I now turn on the quasar, you can see the lifetime of the quasar here in the blue box. You can see how the quasar starts to ionize its surroundings. The neutral gas fraction in the vicinity of the quasar decreases. And at the same time, we can observe more and more of the flux that the quasar emits. So more of the flux that is being emitted can actually be transmitted through the IgM. And so the amount of transmitted flux that we observe in the spectra of these quasars can tell us something about the lifetime. So how long have these galaxies been shining as luminous quasars? And how long have the supermassive black holes that are located in the center of these host galaxies, how long have they actively been accreting matter? Because it's really this accretion process that powers the ionizing UV radiation. And if we look at different sidelines through the hydrodynamical simulation box, we observe a clear dependency on the amount of transmitted flux, which is here indicated by the proximity zone. So King Cheng gave a really nice introduction about that yesterday. As a function of the quasar lifetime. And you can see a dependency for very short lifetimes. You can see it increases for very short quasar lifetimes. And then the proximity zone size ceases to grow, which is once the intergalactic gas has reached ionization equilibrium with the quasar's radiation. And then we observe an increase in proximity zones again, which is due to the ionization of helium-2. And we can use this as dependency now to estimate the lifetime of individual quasars. And here's just one example. For a quasar at redshift 6, we measure the proximity zone, which is indicated by these red lines here. You can see where it falls in the middle panel. In this case, the proximity zone is quite small. It's only 0.5 megaparsec. We have to make sure that it's not prematurely truncated by Lyman limit system or DLAs along the sightline. And this is the posterior probability distribution function for the lifetime of this quasar when marginalizing over the proximity zone measurement. And in this case, is actually quite small. And so we did this for a large sample of high-redshift quasar spectra. And I just want to show you briefly how these compare to the literature one. So what you can see here is the lifetime of these quasars as a function of redshift, so measured for different at different redshifts. And these are all the measurements that my collaborators and I have conducted over the last few years based on this approach by looking at the proximity zones. And there's 3 things I think you can see in this plot. The first one is we're now able for the first time to actually measure these lifetimes of the very early universe for very high redshift quasars, which was previously not or very hardly possible. Then most of the measurements seem to suggest that the mean quasar lifetime is somewhere between 10 to the 6 or maybe 10 to the 7 years or something like that. And there's a population of very young quasars present in the early universe, which has not been detected previously yet. And we estimate there's about 5 to 10% of the quasar population at large, and these are at these early cosmic times that show these very short lifetimes of only about 10,000 years or less. So what consequences do these results have on this growth of supermassive black holes? Well, in a simple model, we can assume that the black holes grow exponentially, starting from some initial black hole seed mass during the lifetime of the quasar. So while the galaxy shines as a luminous quasar. And this growth happens on a characteristic timescale, which is called the salpeter timescale or E-folding timescale, which is about 45 mega years if you assume that the quasar is shining at the Eddington luminosity and with a radiative efficiency of about 10%, which is the fiducial parameter that you get from accretion disk models. And you need about 16 of these E-folding times to grow a billion solar mass black hole from a stellar remnant initial seed, which is orders of magnitude longer than the quasar lifetimes that we measure. So to illustrate this problem a bit more clearly, if we look at the black holes in the center of some of the most distant quasars that we know today, they all host about billion solar mass black holes. If you now assume that they have been growing exponentially at the Eddington limit throughout the whole Hubble time, you can calculate back what the size of the black hole seeds must have been by the time they started growing. And then there's various theories that predict these initial black hole seeds with a range of different masses. And so at the moment, this all looks consistent. But if we now reduce the lifetime of these quasars to only like 10 to the 6 or 10 to 7 years, you can see the age here, which is the average estimate that we obtain for the quasar population at large from our proximity zone measurements, you can see that there's almost no time for these objects to grow a billion solar mass black hole under the current assumptions. And so clearly, the current model is not really working well with those results, and we have to make some adjustments. Okay, so what could be going on? Well, first, our results might provide evidence for very massive initial seeds, for instance, from direct collapse black holes or primordial black holes, rather than stellar remnants. Another option is that maybe quasars have multiple epochs of black hole growth, so they can flicker on and off, and quiescent galaxy phases would alternate with the luminous quasar phases during which the black hole growth is happening. So basically saying the duty cycle is much longer than the lifetime. We could have obscured quasar growth phases, where the radiation from the UV radiation from the accretion disk is obscured by dust. Or we could have very radiatively inefficient accretion, which is often slightly confusingly called super Eddington accretion. And this would reduce the salpeter time, and we could indeed grow a supermassive black hole in very short amount of time. And we have reasons to believe that while these first two options, they can alleviate the tension a little bit between the lifetime that we observe and the mass that needs to be accreted in that time onto the black hole, they cannot account for the complete discrepancy that we observe. But these last two ideas, we believe, are very promising to explain the rapid growth of supermassive black holes in the very early universe. And young quasars that we discovered, or the quasars with these small proximity zones, now present a unique opportunity to actually testing these hypotheses. And in the last few minutes, I want to share you just one of our ideas on how we're planning to test these hypotheses in the future. So I mentioned that on one hand side, our results can be explained by radiatively inefficient accretion, implying that we can actually grow a black hole much faster than expected from accretion disk models. So more of the accreted mass ends up being on the black hole and less is being radiated away. And this implies that these young quasars, or the quasars with short proximity zones that we see, recently observed a change in the accretion rate. So the quasar that we observed today could have been a quiescent galaxy just like 10 to 4, 10 to 5 years before our observations. On the other hand, the quasar could have been shining and growing its black hole for a much longer time, but it was just obscured along our sight line until like 10 to the 4 or so years ago. Then the obscuring clouds moved away and we would observe a quasar as if it were young, but because the UV radiation along the sight line was blocked. But in reality, this quasar has been emitting ionizing radiation and accreting mass onto the black hole for a much longer time. And these two scenarios result, as I said, in like a very similar spectrum, namely showing a small proximity zone, but the emission perpendicular to the line of sight would be different. In the transverse direction would be very different. So in one case, it would be extended if the quasar has been shining in the unobscured direction for a longer time, whereas it would be truncated if the quasar would actually have just turned on. And this is something that we believe we can actually observe in the future. And so if we look at the surface brightness profile of the extended nebular emission lines around these young quasars, or these quasars with small proximity zones, in one case, they would be more extended if we actually have obscuration happening, or in the other case, it would be truncated if the quasar has actually just turned on. And either case would actually be really interesting, because if that's the case, there's actually a significant fraction of black hole growth that should happen in the UV obscured phases, dust enshrouded phases, and there should be a large fraction of obscured quasars in the high redshift universe. Whereas on the other hand, if the profile is truncated, that implies that the quasars are actually young, their nuclear activity has just started, and that provides opportunities to now study the triggering mechanisms, what determines when a galaxy transitions into the active luminous quasar phase. Is that caused by a merger? Where does the fueling material come from? Are there strong in and outflows, and so on? And we have some reason to believe that this latter scenario is actually what's happening, because we have some data from MUSE on the VLT, where we looked at 30 quasars at high redshift, and then we subtract the PSF, and basically what remains is the extended emission. And from these 30 quasars, we have 3 that show these small proximity zones. And interestingly, none of them shows any extended emission. However, these observations or part of them are really shallow, so it could just be that we're like below the surface brightness limit. And so in the future, we want to do this from space, where we can get higher resolution data. So that means we can resolve the emission closer to the quasar. And most importantly, we have access to infrared emission lines and not just to Lyman alpha. And I'm just going to leave up my summary and thank everyone for listening.
All right, thanks, Christina. There are a few questions in the, on Slack. Let me start with one. You mentioned Lyman limit system, but how do you rule out that quasar near zone is set by a nearby Lyman limit system in the data?
Right. Yeah, so we have to rule them out because, well, first of all, Wan Ching gave a really nice talk yesterday where she said that, like, if they are truncated, it can pretend like it has a small proximity zone, but the quasars are actually older in real life. The way we're doing this is, I think I have a plot here, the best we can, basically. So we're putting an absorption or hypothetical absorption system at the end of the proximity zone, and we search for whether, if there were an absorption system, whether we would see any of the low ionization metal lines that could be associated to the system. And so you can see that in this bottom panel here, where we look at silicon-2 and O1 and so on, and just search whether around this line or around this hypothetical absorption system, we see any evidence for metal lines. This is the stack, and you can see, like, well, there's not really any other evidence. However, we cannot rule out very metal poor systems. And so the second experiment we're trying to do is look at the Lyman series forest, because if there would really be a self-shielding dense absorption system, it should be line blank. It should be like absorbing all flux in the forest. So not only in Lyman alpha, but also in the Lyman series. And then sometimes we see some flux in that area, and then we can set a limit on the column density. And yeah, so we're trying to rule that out as best as we can, basically.
All right, thanks. Well, actually, the next question came from Huan Qing. How are the ages of the individual redshift 3 quasars measured? At
redshift 3 is it's the helium-2 Lyman alpha forest. So we're looking at the okay. Helium-2. Right.
Another question: have you looked into the impact of mergers on the growth of supermassive black holes?
Yeah. So I haven't personally, but we know that they don't play, like, they happen, but they can't account for the majority of the black hole growth. So. And there's actually a paper that just came out recently with Fabio Pacucci, and they looked at, basically what they're doing is they look at the quasar luminosity function, because the idea is that the emission from the quasar can be directly translated into accreted mass. And they look at merger trees from hierarchical assembly model, and they compare that. And they, the solution is that in most of the black hole growth throughout the history of the universe, accretion is the dominant process, apart from very high redshifts and very low masses. So at the very, very low mass end, so 10 to 4 solar masses or so, there's a lot of mergers happening, but they can't account for the bigger part of it.
All right, just one last question. Fahad asked, can you comment on the radio transfer models that you're using to estimate quasar lifetime? Yeah, so these are the models that are based on Fred Davies' paper from 2016. So it's post-processing, is a 1D post-processing that just takes heating and cooling into account and is on top of the hydrodynamical mix simulation. Yeah, I think that's the main info, but I can add some more in the Slack.